Dear colleagues, my name is Alexander Nikitin, and today I have the pleasure to present you the work with the title A Multimodal Approach to Modeling the Progressive Fatigue Damage Accumulation. This work is supported by the Russian Science Foundation. The outline of my presentation is following. The key points are results for age-like and central-like fatigue crack growth modeling. Usually, when we are calculating fatigue life, we use the elastic finite element analysis together with the applied stress field. Based on the calculated strain, we can introduce different model of damage accumulation. Traditionally, to predict fatigue life of the structure subjected to the complex loading, the multi-axial fatigue criteria is used. Nowadays, there are many different fracture criteria that are based on different principles, such as stress or strain-based approaches, and use different ideas. The examples of stress and strain-based criteria are shown on this slide on the right hand. The basic ideas are usually related to the driving mode of crack opening. For example, the Smith-Watson-Topper or SVT criterion is developed for normal crack opening, while the stress-based Crossland criteria is developed for the shear crack opening or mode 2. Most of such criteria are formulated for a given loading condition only, I mean for low or high cycle fatigue. Some of the criteria are developed so that they can take into account the loading history, but they are mainly not aimed to switch between different loading regimes automatically. The study on the in-service fatigue failure of different engineering elements shows that fatigue crack often initiated under one loading condition or regime and then turns to the propagation under another one. The most demonstrative example of such behavior is the crack initiation in turbojet engine blades. At the initial stage, it can be provoked by high-frequency vibration leading to the very high cycle fatigue loading. Once the crack-like defect appears, the later stage of crack propagation is driven by the high cycle fatigue loading condition. Obviously, the kinetic parameters and therefore a corresponding fatigue life will be different for these stages. This work introduced a multimodal approach and numerical algorithm for calculating the progressive fatigue damage accumulation and failure with respect to the loading mode based on the stress amplitude. In order to describe a full SN curve, the multimodal approach is used. The main idea is to distinguish three different regimes with its own mechanism and description of the fatigue damage accumulation by an individual laws. The changing in mechanism is not sharp, that is in good agreement with the physically based researches of fractures or processes. Between the regimes can be introduced the bifurcation area where two different mechanisms are existing. A specific method of choosing the damage mode in such area should be established. In the present work, the uniform relation between stress and number of cycles, like a Baskin-type equation, was used for all three regimes, but the parameters of the curves were determined for each range, low cycle, high cycle, and very high cycle fatigue individually. The two parameters kinetic model of fatigue damage accumulation was used. The parameters are alpha and gamma determine the damage accumulation rate. In order to simplify the analytical solution for the damage function, the following link between these parameters are chosen. Alpha equal 1 minus gamma. In order to describe the evolution of fatigue damage in metal, the following kinetic damage equation were used for the low, high, and very high cycle regions. The associated criterion for the function are presented below based on SVT criterion. The parameters of criterion such as ultimate tensile strength, fatigue endurance in the low, high, and very high cycle fatigue ranges are taken from the uniaxial tensile and fatigue test. The numerical algorithm can be separated on 4 different steps. At the first step, we perform the elastic finite element analysis under a given applied stresses. At the second step, we can specify the branch of fatigue life depending on the calculated stress amplitude. It is important to outline that the local stress can be higher than applied microscopic stresses. This can lead to the switch between fatigue curve branches at different stages of numerical calculation. The third step is calculating of damage function for each element and choosing the elements where the value of damage function is exceeding a given value. At the last step, all elements where the damage function is exceeding the given value are deleting from the numerical model. So this procedure can lead to introducing stress concentration factors to the model. After that, the elastic analysis is repeated again for numerical model with the deleted elements, and this procedure will be repeated up to the final fracture of the element of structure. The details of damage function calculation are presented on the slide. The calculation of the function are realized by using self-developed patch that is integrated in the ANSYS software and use a calculated stress field by using finite element methods. The calculation for progressive fatigue damage are presented on this slide. The notch specimen was subjected to ultrasonic loading in order to get the crack-like structure and developing zone of the fatigue damage accumulation here. At the beginning, the local stress were below the classical fatigue limit, and the driving mechanism was associated with very high cycle fatigue region. After the certain length of crack-like structure, the mechanism was turned to the propagation in the high cycle fatigue region. The total fatigue life was calculated based on 2 steps. The first step of initiation and early growth and propagation in high cycle fatigue. The results of the fatigue life for such specimen are presented on the figure on the right. The blind points are corresponding to the experimental data, and the open circle are calculated results. So as we can see, we have a good agreement between the experimental and numerical simulations. The same procedure was realized for another stress ratio R0.5, and we can see similarly the good match of the experimental and numerical data. The results of damage function calculation for the specimen with a central hole subjected to cyclic loading is presented on this slide. The experimental data were taken from the paper of Marmy and Duchesne, multi-axial fatigue damage modeling and macro scale of titanium alloy. As we can see, the results of numerical simulation and experimental data are in good agreement that is similar to previous case of edge-notch specimen. Finally, the following conclusion can be stated. The proposed multimodal approach and numerical algorithm was applied to calculate the fatigue life of central crack and edge-notch specimen made from titanium and aluminum alloys. The results of calculation are in good agreement with the experimental data. The proposed model can be applied to predict the crack path together with the fatigue life. The proposed approach takes into account the loading history, including the switch of the loading regime from low, high to very high cycle fatigue range. The results of calculation shows a good agreement with experimental data obtained for both loading parameters from the stress ratio R-1 to R-0.5. The proposed approach can be applied for different structural materials, from aluminum to quite strong titanium alloys. And also a uniform numerical method has been developed that allows a thorough account calculation of the damage zone development and crack-like defects formation in a material under the cyclic loading. The proposed method does not need explicit identification of the crack in their classic sense. Thank you for your attention.